So anyway, this is 5.1 to 5.4. Actually 4.8 to 5.4, because 4.8 is antiderivative, so you know how to take this antiderivative already. Then 5.1 is area, right? So we know we're going to get this area under the curve. Let's take a quick picture of it. Right, I know it hits a height of 1 and goes through the axis at 1, right? And so, but I'm going all the way up to 5, 2, 3, 4, 5. I'm getting the area under the curve, so that is this area. And I switched my colors, but that's okay. And this area. Right, area under the curve. Oops, sorry, that's not true. Yes, it is. Oops.
And I guess a little bit to the left of, oh no, 1.
No,
Okay,
yep. Oh, so no red area, only green area, and that's all negative. Negative area is underground. Right? Negative x values are left, negative y values are down. This is it. Area under the curve, bound between the curve and the x-axis. So the antiderivative piece is what? What's the antiderivative piece? How do I do this antiderivative, this integral? Well, I'm going to remember I have a slope of 1. I have 1 minus x squared as my derivative, right? So what's the antiderivative of 1?
X.
Good. And the antiderivative of negative x squared. I'm going to add 1 to the power and divide by the new power. The 5.2 piece is called the definite integral, where I evaluate that at 5 and then 1 and then subtract it, right? So this is 1 and this is 5, and that's going to give me the area under the curve. So what do I get here? I get x minus x cubed over 3 evaluated at 5 and 1. So I get 5 minus, what is that, 125 over 3. Yeah, minus 1 minus 1 over 3. So this piece that I'm doing, this piece right here is 4.9, right? Antiderivative is 4.8. This is 5.1, area under the curve. We estimate it in 5.1 using rectangles only. We're going to still do that. And then this piece is 5.2, the definite integral. .3 is Riemann sums. 5.4 is the fundamental theorem of calculus, that the derivative and integral are inverse operations from each other. So what do I get here? I get 15 over 3 minus 125 over 3 minus 3 over 3 plus 1 over 3. So I get negative 110 over 3 minus 2 over 3. I get negative 112 over 3. And of course I can get a decent decimal there. .3 repeating, right? How are we doing there? We okay? This is the first question on your test for chapter 5, right? We can double check this, so we're going to know chapter 5 is correct. Again, we'll know chapter 4 is correct. We know how to check everything. We know how to check everything, and we will know how to check everything in chapter 5. Now we even know how to check things in chapter 3 by looking at the graphs, right? So let's go to my calculator here. And in the y equal, I'm putting in 1 minus x squared. I want to make sure I have a graph that I can see my bounds. The lower bound is 1, the upper bound is 5. I want to see the bounds of the integral. There's 1, 2, 3, 4, 5. I don't have to see all the way at, underground all the way. I don't need to see the y values. I need to see the x values. So I'm going to use the calculate button. So second calculate. I'm going to calculate number 7, the integral. So hit 7 and hit my lower limit of 1 and hit enter, and my upper limit of 5 and hit enter. And there it is, negative 37, 3 repeating. Did I have that right? Yes, negative. I knew there was something wrong. Yes, Afsoon.
That time it gave a good answer.
Could you repeat the
Process, yes.
steps?
Yes. I just lost. Where's my mouse? Here it is. Sorry. Give me 1 second. Okay, calculator steps again. And what I'll do is I just want to clear out my y equal. Just so I will show the whole thing from the beginning again. Otherwise you'll see some remnants of what I just did still on the screen, so it could be confusing. So in y1 I put my function as 1 minus x squared. Even though it's multi-term, I don't need it because I'm just looking at the graph of that function. I want to make sure I see the graph, and for the problem I'm going to give you, Zoom Standard will work. I want to make sure I can see 1 through 5. I want to see the bounds of my integral, right? You can see the bounds of my integral here, right? From the integral from 1 to 5, or evaluate from 1 to 5, right? You can see those bounds here on my screen. So I go to second calculate function, and I hit 7 for the integral, and I hit 1 for my lower bound and 5 for my upper bound. And there's the area, and there's the answer, negative 37.3 repeating.
Thank you.
You're welcome. So it's nice that you're going to know you have this first problem correct when you do the test. And what's our second problem? Well, we want to show that negative 37.3 repeating, I like the 112 over 3 better, sorry. The negative 112 over 3 is equal to the limit as n goes to infinity of the sum of I equals 1 to n of the rectangle's areas, right? The sum of the areas. So that's f of x sub I times delta x. And we have memorized one that we're going to only use right-hand side triangles, rectangles. In Calc 2, we'll do right-hand side, left-hand side, midpoints, trapezoids, and Simpson's rule. So I just need you to know one of these before Calc 2, trying not to torture the students who don't have to take Calc 2. So delta x is equal to b minus a over n, and x sub I is a plus delta x times I, right? So for us, this is in general. And then for us, we know that delta x is 5 minus 1 over n, 4 over n, right? And x sub I is 1 plus 4i over n. Remember, I'm just going to take delta x and multiply by I. Multiply it by the index, not the complex number, right? We don't do any complex numbers in calculus. Until the math majors take complex analysis, which should be a 300 level class when you transfer. It's beautiful. It's such a beautiful thing when you allow complex numbers into calculus. So what do we get here? We get the limit. Is everybody with me? Everybody with me here?
Mm-hmm. You?
Okay, good. Off soon, question?
No, I just wanted to hit the thumbs up. Okay.
Gotcha, no problem. So I'm looking at the limit as n goes to infinity of the sum of I equals 1 to n of the rectangles. Oh, I need f of x sub I. That's usually the part that's tough, which is 1 minus x squared, right? But what am I putting in there is x sub I, so 1 plus 4i over n. And I tend to want to simplify that before I go into my limit. So 1 minus 1 squared plus 8i over n plus 16i squared over n squared. I'm just foiling in my head there. And the 1's cancel, so I get negative 8i over n minus 16i squared over n. Make sure you're with me there.
And we're keeping it as n because it's easier?
I don't think it's easy, no matter what I do. But I'm keeping it as n because I want to possibly give an estimate or actually do the limit.
Okay.
So now I'm going back to my function evaluated. So that's minus 8i over n minus 16i squared over n squared times, that's the height of the function. Now the width of the function is 4 over n. Now you can do your algebra any way you want. You don't have to do the algebra the way I'm doing it. I'm trying to do a very, very simple step every time, especially on the test. And I'm trying not to go too fast because it's very easy to make mistakes on these. And if you make one little algebra mistake, you're not going to get the same answer. The trick is to not panic when you don't get the same answer. We already know we have the right answer because the calculator gave it to us and we verified it, right? So we know we should get the same answer again, and you're probably going to make a mistake. So you'll spend a little time looking at it. You'll do the rest of the exam, and then you'll come back and start brand new, right? And see what happens. And if it was 10 points and you did everything right but missed like a sign somewhere, like a plus or minus, right? I'd probably still give you 8 out of 10. So we want to distribute here. And again, I'm trying to go slow, trying not to do too much, because I want to make sure you see this, that I've got negative 32i over n squared minus 64i squared over, this is an n squared here, sorry. Yep. Over n cubed. I don't know if you can see it, but I can pull out the negative all the way out of the limit here. So I'm going to pull out that negative. I know the answer is negative, right? So I'm pulling that out. I'll wait till I see if I get my 112 over 3 for the positive, and then, of course, negate it at the end. And then I can also see that I'm going to have two sums, 32 over n squared times the sum of I, and 64 over n cubed times the sum of I squared. How we doing?
Process a little overwhelming, but we'll get there.
You're going to eventually have to, and I'm not just talking to Jesse, but I'm talking to Jesse. You're eventually going to have to write this down. You can't just look at it. You have to write it down. You have to make mistakes. You have to ask for help. Okay?
Right.
Now we have a formula for the sum of I and a formula for the sum of I squared, right? And you can see what I'm building up a quadratic here. So of course I need something for I squared because it's representing x squared. Okay? So I've got the opposite of the limit as n goes to infinity. of 32 over n squared times n plus 1 all over 2 plus 64 over n cubed times n plus 1 times 2n plus 1 all over 6. We do a lot of this in Calc 2. So you're taking Calc 2, you're jumping on this now, because if you blow this off in Calc 1, when you do it in Calc 2,
yeah, there's a shipwreck up ahead if not.
in two different sections, in Chapter 5 and in Chapter 8. Eventually, we learn that we run out of methods of integrating, and so what we do is turn everything into polynomials.
Why does it turn positive?
The negatives out here. I factored that. I could see.
I see.
Yeah, I could factor that negative out. And remember, my sum is dependent upon I. My limit is dependent upon n. So the -1 can come out completely, right? It's not. There's no dependence on -1, a factor, a numeric factor.
You can take negatives out pretty easily unless they're under a square root.
Coefficients. No,
Yeah.
Square root of 5 would come out too. So coefficients.
If the negative was inside of a square root.
Well, no, we're not going to have that. We don't have complex numbers in calculus. Yeah.
Okay, yeah. I'm just like noting mentally out loud almost.
Yes. I want to simplify this. Go ahead, Jess.
We wouldn't have a question like that, but if it were there, then yeah, you couldn't do that.
It won't be there. It won't happen.
Yeah.
So
Fair enough.
I want to simplify this. I've got, it looks like my 32 and my 2 cancel to a 16, and my n squared cancel to an n. So I've got a 16 over n times an n plus 1. And I'm going to distribute that. But I want to do the same kind of baby step on the other one. So it looks like I have 32 over 2n squared, right? The 64 and the 6, oh, by 2, sorry, there's a 3n squared. And n cubed go to n squared. And I'm going to distribute this piece, 2n squared plus 3n plus 1. So I FOILed out this piece. Just let me go. Let me take a 1 minute back in one.
We good, Professor? Remove. I think he went and checked something and got interrupted.
No, I had when my dog goes for a walk. This started in COVID. It's weird. I'm sorry to have to admit it, but we wash her feet off when she comes into the apartment. So I just had to go get a soapy towel for my girlfriend to do that right when they come in the door. Sorry about that. Is everybody caught up with me?
Yes.
So
Fine.
I want to distribute now, and I'm going to try and simplify as I do it. So I get a 16n times n plus a 16 over n times n and a 16n over n. Sorry, I'm not going to simplify why I do it. I can't. I've got, oh, this one I can. 64 n squared over 3n squared plus 96n over 3n squared plus 32 over 3n squared.
Nice big polynomials.
Yeah, so the ones that I'm really interested in are the ones that are going to just turn into constants, right? So you can see here I have minus the limit as n goes to infinity of 16 plus 64 over 3 plus 16 over n plus 32 over n plus 32 over 3n squared. Because I know when I take a limit at infinity and my denominator dominates, meaning the power of the variable in the denominator is bigger than the power of the variable in the numerator, all of those limits go to 0. So now I have negative times the limit as n goes to infinity of 16 plus 64 over 3 plus 0 plus 0 plus 0. Oh, the limit's gone. Sorry. Right? I took the limit. So I have negative 16 minus 64 over 3. Uh-oh. Yes, Upson.
So I get how the 16 over n and 32 over n became 0 because it's just power of 1, but how did we, what was your explanation for the 32 over 3?
So the downstairs, yeah, the downstairs power is n squared, right?
Mm-hmm.
Upstairs is just a constant. So
Yeah.
So think about when n is 10, I'm dividing now by 300.
Okay.
Right, so this is still going to go to 0.
Okay.
Yeah.
Because
And you know 1 over
value.
you know 1 over n squared looks like that. So when I'm going to the right, what's the height going to?
Okay.
Yeah, right.
Okay.
Yep. So minus 58 over minus 64 all over 3. Oh, that's it. Don't I have a mistake? What's 3 times 6? Oh, 18. Silly Robert. 48.
It happens.
And there it is, minus 112 over 3. Check.
Thankfully, it was a small mistake at the end, not a small mistake in the middle.
Exactly. Small mistake. We don't want it to happen at all, but as engineers, we build
We
in.
have to do this for the
in.
tests.
Yeah. Yes. Yes. Almost everybody gets it right, but if you don't practice, you don't get it right.
That's why I was practicing, and I felt what you said when you said that we have to write a lot.
Yep, it's a lot of work. And you don't have to do your algebra in such basic steps as me, but until you are not making mistakes, I would suggest doing things as simple as you can. So there it is. 6.1 to 6.3 is really that problem, right? 6.4, I like just to talk about it, and I already have, right? 5.4 is the fundamental theorem of calculus. and we've been doing it. Comes in two pieces. That if I take the integral of f prime of x dx, I get f of x plus c, right? And if I take the derivative of f of x plus c, I get f prime of x. So you can really see I'm just trying to show that these undo each other. They're inverse functions, right? Inverse operations. So part one is that the integral and the derivative are inverse operations. Part two says that the integral from a to b of f prime of x dx gives me the area under the curve of the antiderivative, that's f of b minus f of a. So that's saying two things as well. It's saying if I take a derivative of a function, I get the slope of the function. And if I take the antiderivative of the slope of the function, I get the area under the curve found using the original function. Weird. It's unbelievable, honestly. But this is 3.4. Sorry, 5.4, fundamental theorem of calculus. And what I'm saying is you're already doing it in the first three problems, right? You're using this piece in that 5.1, 5.2, 5.3 problem that we just did. So I think we're ready for some 5.5 because that's the tough piece. And we basically will have 3 classes. After the exam, we'll have 3 classes of 5.5 work. Then review for Chapter 5 test. Take the Chapter 5 test. Review for 3 classes of the whole course, and then take the final exam. Right? That's our schedule. Pretty quick. It's going to go pretty quick. So we could do one of two things. We could do another problem like we did today, 5.1 to 5.3, or we can move on to 5.5. What do you think?
Another problem?
Another problem from 5.1 to 5.3. And know that you can do these yourself. You can do a real simple problem and make it up yourself, or you can go grab some problems from my old exams, right? Chapter 5 exams, final exams, or you can make your own problem up. I mean, making your own problem up is kind of nice. You can do an integral with an mx plus b, right? We did one of those already. You can do an integral with a quadratic. We did a simple one. We could do a more complicated one, right? Of an ax squared plus a bx plus c. Or anything in between there. So some terms missing, right? I tend not to give an x cubed. I tend not to give an x cubed. And I'm sure I'm not going to give an x cubed this time. But let's do an x cubed anyway, just for fun. But let's make it real simple. Let's just integrate x cubed dx, right? Let's say from 0 to 3. Okay. So what do we get?
You have to get the underneath and then add a power. Oh.
Yeah. So we're going to get that area. But how are we going to get it? How do I integrate x cubed?
Plus 1 over...
Nice, plus 1 all over 4. Exactly. And I don't care about the plus c because they're going to cancel when I subtract the two. right? I'm going to get f of 3 minus f of 0, and then subtract them. And when I subtract, the c's go away, so we don't even put it in. So this is now x to the 4th over 4, evaluated at 3, and then evaluated at 0, and then subtract. So I get 3 to the 4th over 3 minus 0 to the 4th over 3. I think that's 81 over 3. Is that right? Yes. And then 3 goes into 81. Yes, Upson.
So how do we? I thought we put x to the 4th over 4 because that's the antiderivative.
Oh my
and
God!
then
Oh my God! Robert. Oh my God! Thank you. So much for having a nice fraction. That's right. 81 over 4 it is. Nothing wrong with fractions. Thank you, Upson. Saving me hours and hours of frustration. Okay, there is my definite integral. What's the definite integral give me? The area under the curve, right? The other integrals we do are called indefinite, where I just get a function, or antiderivatives. I just get a function. I don't get a number, right? But I'm just going to say integrate in both cases. If there are bounds there, you know you're supposed to get me an area. If there are no bounds there, you're just getting me a function plus c. Okay. All right. Now our limit. We want to show that this is equal to the limit as n goes to infinity. Nice infinity symbol. Of the sum of I equal from the first rectangle to the last rectangle of the sum of f of x sub I times delta x. And we know for our case delta x is 3 minus 0 over n, which is 3 over n, and x sub I is 0 plus 3 over n times I, which is just 3i over n. Right, just 0 plus my lower bound plus delta x times I, times the index. And f of x sub I, in this case very simple, is x cubed, right, or x sub I all cubed, 3i over n all cubed. So that's 27i cubed over n cubed. And you can see, well, actually, if I remove this limit part, it's kind of interesting. 81 over 4 will be approximately the sum of I equal 1 to n of this f of x sub I times delta x, which is what? 27i cubed over n cubed times 3 over n. And you can already see it, right? You can already see something that's quite interesting here is I've got an 81 I cubed over n to the 4th. So that 81 is obviously the 81 in the answer, right? So this is 81 over n to the 4th times the sum of I equals 1 to n of, oh, that's an I cubed. I cubed. And we have a formula for I cubed. Don't let me go too fast. 3, 6, 9, 12, 15, 16, 17. One student missing.
I'm here.
Abraham. Abraham's missing. Our formula is n squared times n plus 1 quantity squared over 6. No, sorry, 4. Thank you. Oh, look at that. You see my 81 over 4 right away, right? This is the n plus 1 squared, sorry. So I have 81 over 4 times n plus 1 quantity squared over n squared. I'm going to FOIL that out. But before I do, I get a nice estimate of the area here. So before I FOIL that out, let me show I get a pretty nice estimate for the area. So I'm going to use 10 rectangles, then 100 rectangles, then 1,000 rectangles. Okay.
Just a Riemann sum.
Yeah. The whole thing with the limit is the Riemann sum. This is an estimate. Yeah, using the rectangles, Riemann sums. Riemann sums are a little bit more complicated than just rectangles. It turns out I could use any shape I want to estimate the area under the curve. Let me just, I want to turn on Excel. I want to make sure I don't show my gradebook. Give me 1 second. Just going to stop my share real quick.
Here's the part where I joke that the OSINT guys are looking at your sunglasses and analyzing.
All right, so I want to build up tens for my x values. Sorry, my n values. So n is my number of rectangles, and I want to start at 10, and then I want to go to 100. So equals 10 times a2. So there's 100, and then I'll go to 1,000, right, etc. Oops, didn't work. Oh, I know why. Because I did the wrong thing. All right, here we go. So there's my value of n. I want to look at the estimate, right, the area estimate. So the area was what? Equals 81 over 4 times n plus 1 quantity squared, right? But n is coming from a2. So a2 plus 1 quantity squared divided by n squared, so a2 squared. a2 squared. And I know my actual area, right, was 81 over 4. Because I want to fill those down and see what happens. See how long it takes me to get there. I mean, so look at after 100,000 rectangles, if I round to 2 places, I'm there, right? So pretty damn quick. But now I could fill down. Does everybody understand what's going on here? What did I do? How did I do that? That's fine.
It's dividing by a bigger and bigger number.
Yeah. So I just want to fill down here. So let's see what happens if we do this 20 times, 19 times, Control D. And so look at after the 7th version of it, which is 1, 2, 3, 4, 5, 6, 10 million. After I get to 10 million rectangles, I get the actual area, right? So not even to infinity, a lot sooner. And this is based on me rounding to, what, four decimal places, 5 decimal places. So really quick, right? So for like the approximate area for 10 rectangles, right, would be what? 10 plus 1 quantity squared over 10 squared. So 81 over 4 times 121 over 100. Right? 81 divided by 4 times 121 divided by 100, 24.5025, and of course 81 over 4 is 20.25. And remember, I'm getting over estimate for my right-hand rectangles in this case. So just looking at this piece again, right? 81 over 4 is the limit as n goes to infinity of 81 over 4 times n squared plus 2n plus 1 over n squared, right? And you could see that my first term, when I distribute, the n squareds are going to cancel, and the other two terms are going to have an n squared or an n under the denominator, right? So I'm going to get 81 over 4 plus 81 over 2n plus 81 over 4n squared, right? And the limit on those last two are 0.
Yeah, my question, Professor, is how did you get 81 over 2n?
Yeah, when I distribute it to this middle term, the 2 and the 4 cancel, the 81 survives, and an n survives.
Okay, thank
Yeah,
you.
so I'm distributing to those 3 to get this one. Yes, Hapsu.
So I get all of the math, but I need the concept again. So what does n stand for?
Number of rectangles.
Oh, that's okay.
Yeah.
That was
So when I went from 0 to 3, what did I do? 0 to 3? Yeah, right? I can see if I just had 3 rectangles, right? Just have 3 rectangles, I'm getting the sum of that area. Now, if I double the rectangles, right? If I double the rectangles, you can now see my the extra area now is just these little pieces of green. So you see I'm getting a better estimate, right?
yeah.
So it's just, yep, n is the number of rectangles. And I is an index, meaning the first rectangle, the second rectangle, the third rectangle, the fourth rectangle, the fifth rectangle. So I is just the counter.
I'll look that up. Thank you.
Yep. Good question.
Professor, I have a question.
Yes, Chima.
What is the reason why you did the area of 10 rectangles?
I just chose 10. I just picked 10. That's typically like the book will do 4 and then 8 and then 16. I just picked 10.
So they tell you what rectangles you need to...
Yeah, I could ask you just to give me an estimate for 4 rectangles. What's the area under the curve? But the process is the same, right? But when you're approximating the area, you're just putting an n value into here. And when you're getting the actual area, you're taking the limit as n goes to infinity.
Okay, thank you.
Yes. And you can see in my same picture here, my my x cubed piece, right? If I do 100 rectangles, it's really hard to see the error. The error is so small, it's really hard to see that area, right?
Yep.
Nice. Nice. We can leave the last section of our semester till next week. So tomorrow, Wednesday, we will review. Please have questions ready for me to do. I'll tell you right now, our list for our test is I'm just going to have you do an abs min max, right, of f of x on closed interval, right? I'm going to have you find critical values of a trig. I'm going to have you find increasing, decreasing intervals first derivative test. I'm going to have you find first derivative test for local min and max. What I'm doing here is I get to give you different functions, right? So instead of giving me a first derivative test for one function with the intervals and the local min and max, I get to pick two functions now, right? Because I really want to make sure you can do derivatives. I want to do a second derivative test for concavity. And inflection points. But not for a second, not for local min and max. And then a geometry optimization problem. And then a min distance optimization problem. And that's it. That's going to be your Chapter 4 test.
This is for Friday,
Friday,
right?
Yep.
Okay.
And you can do all of these. You can do all of these already. Kind of nice.
Professor, could you mark which parts of the chapter he's applied to?
Yes, this is 4.2. This is 4.3, 4.3, 4.3, 4.3, 4.6, 4.6.
Thank you.
Yes.
And that's all it's going to be for chapter 4. There's one from
That's
5 point.
That's it.
5.3 to that's it.
That's it.
That's it. All right.
That's
Okay.
it. That's it. Nothing else. Notice my old tests have 4.1 on them, so don't worry about the 4.1 stuff. When you start seeing dx dt and dy dt and all of that, that's related rate stuff.
Also, what to call it? Would there going to be some questions from chapter 3 going to be put in chapter 4?
Yes. 1, 2, 3, 4 problems from chapter. 5. 5 problems from Chapter 3 test. I'm going to take some functions from the Chapter 3 test and make them into a first derivative test. So you have to be able to do all your derivatives from Chapter 3.
Okay. How many questions going to be on the test?
1, 2, 3, 4, 5, 6, 7.
Oh, 7. All right.
7 questions on every test we've taken so far.
All right. Thank you.
Yes. Soon.
So what we learned today from 5 will be on the next test?
Correct. That's Chapter 5 material. And our antiderivatives are on Chapter 5 as well. So there's no antiderivatives on Chapter 4, even though that was Section 4.8. But I just save it for Chapter 5.
Yep.
Nice stuff.
Professor, I have a question.
Sure.
Is the geometry optimization problem
Yes.
the one with the maximum volume?
The max, like the box where I had to minimize the surface. Yeah, something like that.
Okay, thank you.
Nice. So I think I stopped my screen